starting with one of the paintings on the ceiling of the Sistine Chapel with Adam and the Intelligent Designer, and you'll see that the flying spaghetti monster will play a big role in some of the theoretical things that we'll be talking about in a few seconds. So this is Panorama Research. We're located down here at the base of San Francisco Bay. We've been around for coming up on 20 years. A number of companies have been started in our facility that the SENS Foundation is now a part of. So applied Healthspan engineering. So this is behavioral, pharmacological, biomechanical, and regenerative means of maximizing wellness to increase chronological age and then eventually overcome it, which is, of course, the goal of SENS. And the question is this intelligently designed health? Now, I'm going to present a couple of framework slides to look at the discussion, or to frame the discussion. So this is lifespan here. We see reserve capacity that develops in youth and then gradually deteriorates. Development, vitality, degeneration, and then morbidity. And the goal of Healthspan engineering is, of course, to square this curve. Okay? And of course, here's SENS making it go well into the future. Okay? So the question is, where are we in terms of this? We've heard that since over the last 100 years, the lifespan has almost doubled in many of the developed countries. And where are we now, and how can we improve this further? Now, the logic into that, of course, is what I call a Healthspan pink slip. Okay, and of course, society will need to think about this issue also. So, what is the potential? The longest living mammal is a bowhead whale, the longest documented, 211 years. This was determined by aspartic acid racemization down at Jeffrey Beta's laboratory at Scripps. And this guy gets lots of exercise. It's low impact. Most of them don't smoke. Since Captain Ahab died 150 years ago, they now have a low-stress lifestyle. And maybe there's and they have a low heart rate, lots of blubber. Now, what we think about when we conceive of this are boxes. Think outside the box, okay? And these boxes get smaller as one ages, and eventually one finds himself outside the box where they've got limited reserve. And a good example of that is until the 1940s, when penicillin came around, even a strep throat was life-threatening. And the woman that was first treated woman at Yale that received penicillin lived another 60 years after she was saved by penicillin. It pushed her back inside the box. So the question is, what kinds of technologies, drugs, whatnot can we do to push us and keep us inside the box? And one of the things that we're going to be talking about is reserve. And one of the best documented decreases in reserve over a lifespan is the FEV1. This is the forced expiratory volume, a measure of pulmonary function. Here you see an average non-smoker. If you smoke, you're over here. You can see down here at 1 out of 4 or 5 liters, you will have a noticeable loss of function, and at some point this is incompatible with life. So one question we can ask ourselves is, are there any interventions that increase that reserve? And I think that for Healthspan engineering, that's one of the most important questions. And I'm going to be asking for audience participation in a few minutes to address this kind of situation today, not in 20 or 30 years with new stem cell therapies, things like that. Well, one thing that does this are statins. Okay? And you can see here's a decline. This is the study from Boston, 800 men, average age 71, and they measured FEV1 and forced vital capacity several times in this 10-year period. And what you can see is that statins reduced the rate of decline. Didn't reverse it, but they reduced the rate of decline. I think one of the things that we'd like to understand is how to reverse this. And that would be one of the goals of SENS, of course. And you can see even in some of the recent quitters, and current smokers, that it was even helpful there. So one of the compounds that would certainly be on our list would be statins. And we can ask our MD colleagues about that in a second. So when we were going through this and preparing this talk, Andrew and I wondered, is there any tissue that doesn't grow or slows down with aging? The only thing we could think of is maybe hair, in the nose and the ears. But if somebody has some tissue that doesn't, I'd like to hear about it. Okay, so the framework for the discussion is what's practical today, maybe in 10 years, where does applied healthspan engineering end and SENS begin, and how far are we from true SENS? Okay? I'm going to have just a couple more slides to outline some examples of these things. And for this, to frame the discussion, we're going to use this kind of outline. So here you see what I call a hierarchy of modularity, and we're going to be talking about that in the context of Darwinian evolution or intelligent design in a second. Okay, so we got things like this, physical interventions. So this would be heat, electromagnetic, ultrasound, things like that. We know, for example, that electromagnetic energy can induce heat shock proteins, which has some benefit and may be useful. We know that for certain conditions, sitting in hot tubs or exposing one's respiratory mucosa to heat is very useful for decreasing the frequency of asthma or decreasing the frequency of or the severity of a common cold. Okay, I don't need to tell this audience about diet, calories, exercise, and the benefit of these things. I'll have a few words to say about single molecules. These are small molecule interventions. Okay, these are typical pharmaceuticals and nutraceuticals. There's a lot of interest in this, of course, as a magic bullet for aging. Macromolecules are proteins and other things. Some of these are what I call chaotic. In other words, they're just a mix. And some, maybe there'll be something in the future where they're self-assembled, so-called nanomachines. Next, we have gene therapy. So this is information therapy, okay, antisense, RNAi, things like that. And finally, we get to cellular stem cells, or what we call modular automata. And finally, whole tissues, organs, transplants, and medical devices. Okay. So let me run through just really quickly a couple of examples of these. So this is the hierarchy. If we were intelligently designing ourselves, like the flying spaghetti monster, then we would make this modular. And if you have a broken stereo, you go in and you replace a circuit board or a transistor at whatever level you're at here. Okay? We don't repair whole tires now. We replace them when they're old. Okay? In a carbon-based system, it's a little bit more difficult because of the integration. So Andrew and I came up with this hierarchy of modularity. It extends from photons all the way to whole organisms and ecosystems. And maybe it's artificial. Maybe that's just a way for us as humans to think about this. But when our understanding is incomplete, the best solution is to replace the highest level module available with current technology. Okay, and the caveat of this, and this is the thing I want to talk about in the discussion in a second, is this: in biomodularity, you can have diffuse boundaries. Okay, and that can kind of confuse things, make it more difficult. So you can take a 100-year-old car and keep replacing the parts, and it'll run today as well as it did 100 years ago, unless you don't take care of it, of course. So this guy here really needs some sense. Okay, so this is the critical part of the discussion. So if the intelligent designer, the flying spaghetti monster, had designed organisms, they'd be clean, they'd be modular. However, evolution designs by using already created what's available. Okay? It utilizes emergent properties in self-organization and utilizes potential destructive processes in a constructive way. Okay? As long as reproduction works. What we're concerned about is happening well after reproduction, and that creates lots of problems. Excuse me. And that ends up compromising modularity. Evolution compromises modularity to maintain homeostasis. Now, a good example of this is the body has recruited reactive oxygen species, which are well known to damage cells, to act constructively in a variety